Hi, I'm Amy, and this is my research titled Effects of the Bimaxwellian Plasma on Active Spacecraft Charging in GEO. So, the motivation for this work lies in the fact that the spatial density of objects in GEO is relatively high, and GEO satellites make up for 95% of the total insurance value of all satellites. However, despite the value of the object in GEO and regulations put in place by IADC to protect our assets, around 50% of GEO satellites are non-compliant or just completely abandoned at the end of their lives. The increasing spatial density in GEO has the potential to result in a catastrophic collision with a defunct satellite, which would result in a chain of cascading collisions as the number of space objects increases dramatically. Active debris removal would be helpful to remove the non-compliant or abandoned objects, but debris in GEO tumbles with rotation rates up to tens of degrees per second, making it nearly impossible to grapple with physically. The electrostatic tractor has been proposed as a method of contactless debris removal. Here, there's a servicer spacecraft that uses an electron beam to make the target object electric potential negative while making its own potential positive. This allows the servicer to then pull the target contactlessly into a graveyard orbit. One challenge of the electrostatic tractor is that the GEO environment is highly volatile due to exposure to electromagnetic storms and substorms. Substorms occur every few hours and cause high-energy particles from the magnetotail to be injected into GEO. Since the geoplasma is very low density, the environment ends up becoming a mixture of two plasmas, which make it better modeled using a bimaxwellian distribution as opposed to a Maxwellian distribution. First, I'll briefly discuss charging in a single Maxwellian plasma. The velocity distribution function is shown here, as well as a simplified current balance. The current balance is simplified to better explain the concept of the critical temperature, which is the temperature at which negative charging begins for a particular material. Only ambient electrons and the resulting backscattered and secondary electrons are accounted for in this equation. This figure graphically illustrates the critical temperature as well as the anticritical temperature, which are the two times that the current balance equation shown on the previous slide intersect 1. Previous research has shown that when using an electron beam in a single Maxwellian plasma, the target potential actually has 3 equilibria. The most and least negative equilibria are stable, while the middle equilibrium is unstable. It's possible to jump from one stable equilibrium through the unstable equilibrium to the other stable equilibrium due to changes in the environment or photoelectron emission. So this alludes really well to the concept of the triple root jump, which occurs naturally in a bimaxwellian plasma. The triple root jump is the concept that a spacecraft potential has 3 equilibrium states and may jump through the unstable middle root to another stable root due to perturbations in the environment. It's important to note here that it's possible for the spacecraft to jump from a negative potential to a positive potential. A bimaxwellian distribution is the sum of 2 Maxwellian distributions. The simplified current balance shown here is clearly much more complex than that for the single Maxwellian plasma. Rather than being a function of only the temperature, the onset of charging is now dependent on also the electron density ratio alpha, in addition to the temperatures of population 1 and population 2, where T2 is always greater than T1. The graphs here illustrate the charging threshold for the bimaxwellian plasma. The figure on the left is the simplified analytical solution, neglecting the ion contribution and assuming the initial target potential is 0. Within the U-shaped curve, the spacecraft will be charged positively, and below the curve, the spacecraft will be charged negatively. It is interesting to me that the asymptotes of this curve are at the critical and anticritical temperatures. The figure on the right shows the numerical solution that accounts for the ion contribution. The environment here assumes the electron temperatures are equal to the ion temperatures for both environments and also the same for the electron and ion densities. It's found that increasing T2 causes the electron density ratio required for a jump to a positive potential to increase, indicating that the threshold curve will shift up. Decreasing the ratio of electrons temperatures to ion temperatures causes the threshold curve to shift to the left and also possibly down, which makes sense because the positive influence of the ions in this case would be greater. The key result is that the initial potential of the spacecraft does not affect the threshold curve nor the equilibrium values, which is significant because the initial potential does affect which equilibrium value the spacecraft will converge to when including the electron beam. So when we include the electron beam in the bi-Maxwellian environment at a current of 50 microamps, a jump to positive potential becomes pretty unlikely, except for in extreme environments, as we'll see later. I'm going to show results for two different environments, a more mild environment and a worst case environment measured by the scathe emission. Here on this slide, I'm showing the parameters T1, T2, and N1 for both electrons and ions. N2 will vary with alpha, which is going to vary linearly between values for clarity in the plots. These figures show the results of charging in the mild environments. The figure on the left is showing the target potentials over time starting at various initial potentials. For each initial potential, a range of alphas between 0.1 and 2 are used. The right plot shows a more comprehensive overview of the charging, which is the total current as a function of the target potential and alpha. As we saw previously for the single Maxwellian plasma, there are three negative equilibria, with the outer two being stable and the middle one being unstable. The most negative equilibria is the case where the target is initially charged negatively enough that the electron beam cannot impact it, so it then converges to the electron beam energy, which in this case is 20 kiloelectron volts. The least negative equilibria is the result of the electron beam impact and the resulting backscattered and secondary electron currents. The main observation here is that when alpha is small, the perturbations can cause significant jumps in potential. On the other hand, as alpha becomes increasingly large, the equilibrium potential converges to a particular value. Now, accounting for the servicer, the figure on the left is the same as the one in the previous slide. The figure on the right shows the natural charging of the target from its natural potential initially. When the electron beam hits the target, it initially begins to charge negatively very quickly, as you can see. However, as the servicer spacecraft releases electrons, it charges more and more positively, which causes the electrons from the electron beam to turn around as they're attracted back to the servicer. Then fewer electrons actually impact the target. Since the environment has a positive influence on the charging of the target, the potential converges to a less negative potential than without the effects of the servicer accounted for. In the worst case environment, we can clearly see that there's only one negative equilibrium potential rather than three. Here, small values of alpha cause positive charging, which would make the electrostatic attractor ineffectual. Again, as alpha becomes increasingly large, the equilibrium potential converges to a particular value. So the key takeaways here are as follows. First, as alpha becomes increasingly large, the plasma behaves like a single Maxwellian plasma, so the equilibrium jumps will be more predictable than when the density of population 2 electrons is significantly less than that for population 1. Even when N1 is close to N2, slight changes in electron density can cause the target potential to jump. When N2 is much larger than N1, the target potential can jump dramatically between equilibria. Here, alpha is being held fixed while the temperatures of population 2 are being varied. The leftmost figure shows the results for alpha is equal to 0.1, the middle plot for alpha is equal to 1, and the rightmost plot for alpha equal to 2. The population 2 temperatures for electrons and ions are being varied between the critical temperature, T star, and the scatho worst case temperatures. This simulation supports the previous conclusion that perturbations in the environment cause more severe jumps in target potential when alpha is small. Another interesting finding here is that as T2 becomes closer to the critical temperature T star, the equilibrium potential increases in all three cases. The overarching conclusion of this work is that the electrostatic tractor would be most effective in an environment where N1 is significantly greater than N2. When N2 is greater than N1, perturbations in the environment make charging unpredictable and may even render the tractor ineffective, as the target charges positively. Future work includes modeling the forces and torques generated from the resulting potentials and also simulating the charging in other non-Maxwellian GEO environments, including a kappa distribution, and also a combination of a kappa and a Maxwellian distribution. Thanks so much.